So welcome everybody. Thank you for joining our talk. The aggregate is dead, long live the aggregate. My name is Sara Pellegrini.
And my name is Milan Savic.
And we are a software engineer for a company that is named Axonic. But today we are here in a completely different guise. So we are here with a well-defined target. We are here for kill the aggregate. So for those who are not familiar with the domain-driven design and with the aggregate concept, let me introduce it for you. So the aggregate has always been for me one of the most controversial and weakest elements of domain-driven design. Its definition is quite vague, in my opinion. An aggregate is a cluster of associated objects that we treat as a unit for the purpose of data changes. So how many of you are very experienced with domain-driven design and knows exactly what this definition means? Can you raise your hand? Okay.
Few hands.
Few hands. How many of you have seen this definition for the very first time in this place? Okay.
Okay.
A lot more. And how many of you believes that this definition is a bit cloudy? I can confirm that during our consultancy activity, we verified that the full understanding of the aggregate concept is difficult for many. And it is difficult it is easy to make mistakes, and these mistakes are difficult to be fixed later. So a lot of developers, some percentage of developers believes that the whole architecture is overcomplicated. And we are here to make more clarity about that.
Yes, so Blue Book, once again, will try to bridge the gap between theory and practice. So let's see what it says. That we should cluster the entities and value objects into aggregates and define boundaries around each. We should choose one entity to be designated aggregate root, and all communication should go through that root. So basically all entities or other software components should hold a reference only to the root only. And we should allow those connections to be held to the root only. And with these definitions, we are still not completely sure what is happening, how we should build our instinct, how we should approach when we are designing our system. So we are still unsure what should be done. So what are we going to do now, today in this session? As you may notice, the theme of this presentation is Kill Bill movie. And we chose 5 villains that are going to represent 5 pitfalls of aggregates. And we are going to try and address each one of them.
Yeah, to better understand the criticalities of the aggregate, we want to do together an exercise, an even-storming exercise about educational domain. So the rules are very simple. A course cannot accept more than n students, and n, that is the course capacity, can be changed at any time to any positive integer that is different from the current one, even if the number of currently subscribed students is larger than the new value. In this case, what happened is very simple. The course will not be able to accept any further subscription until a sufficient number of unsubscription has taken place in order to have the student subscribed lower than the capacity again. So let's start identifying the events. So we know that a course can be created, and we know also that a student can subscribe to a course, and that a student can unsubscribe to a course, from a course. We also know that from time to time, the capacity of the course can change. Let's move now to analyze the triggers for these events, right? And in our case, we can simply say that all these events are triggered by requests from the user, so by commands coming from the user. This is pretty simple, right? So far, so good. It's very natural, linear, not complex. And why is that? Because of the storytelling. Because one of the most powerful achievements of domain-driven design, in my opinion, was to break down the barriers between technicians and domain experts, thanks to tools that are capable of exploiting the immense potential of storytelling, exactly like event storming, for example. So storytelling is so powerful because it is innate in human nature, right? You don't need any special competence or skill to tell a story. And it really helps to break down the barriers between technician and domain expert. But in my experience, the fluidity of the discovery process that is very high during this storytelling phase hit a snag when we try to introduce the aggregate into the story. And why is that? Because the aggregate basically is a way to solve a technical problem. Basically is a resolution of a technical aspect of our system, right? The aggregate is the boundary of the consistency, is the guardian of the invariance. So when a change to any object within the aggregate boundary is committed, all invariants of the whole aggregate must be satisfied. The aggregate is basically the component that is responsible for ensuring the strong consistency inside a world, inside an ecosystem that is by nature eventually consistent. But at the same time, it tries to represent a business concept that acts as a guardian for a certain set of business rules. It is very complex to explain this concept to domain experts, to business people, right? And of course, we cannot provide any technical explanation to them. So, as a technician, I need to admit that anytime I need to identify the aggregates, I start clustering, grouping together those data that share the same consistency constraints. And this is why, in this example, all the rules were related to the curse, and I would choose the curse as an aggregate for this use case. So translating this idea into non-technical terms for explaining what it is to business people is not easy. We can use some metaphors. We can ask some questions like, who would you send this command to? Or in which box would you put this information? Or who can guarantee me that this rule is not violated? These are tricks that can help sometimes, but not always are completely effective. So here is the first villain in our story. The aggregate does not fit storytelling. So the introduction of the aggregate into the storytelling breaks the fluidity of the discovery process, because it is an element that does not fit the story. It is us as technicians that we forcefully try to extract this information from business experts to fulfill our needs. And the aggregate was created to respond to a technical requirement. So the business people should not worry about any technical aspect of our systems. But anyway, in a certain way, they are asked to identify exactly these elements that are technical by definition. So, furthermore, the aggregate moves the focus away from the behavior and back to the model, to the old data-centric approach, right? So.
And now we have a second villain in front of us, and that is that aggregate mixes technical and business aspects. Usually when we want to model our domain, we have a mental model in our heads, in our minds, that corresponds to that domain. But what we usually do not have, and maybe it's not so obvious, are business invariants. And sometimes those business invariants can span over several concepts in our domain. And then we try to model that with a single model. Usually does not work out very well. There are different approaches when it comes to modeling. So some people try to take a look at data and see what data changes together. Then they try to group them and then to decide how are they going to form their aggregates. But people make mistakes. Sometimes we make mistakes as well, right? And what are we trying to do? We take a look at our commands, our events, something that is a result of our event modeling session, and we try to search for nouns. What would be the perfect noun in this case, right? Probably the course. And we extract that, and we are going to say, okay, this is our aggregate. We are going as a consequence, to have a course aggregate, it is capable of handling these commands to create a course, subscribe student, unsubscribe student, update course capacity, etc., etc. And it is also responsible for publishing corresponding events to these commands. When it comes to the storage perspective, here we have a course aggregate with a bunch of subscriptions, and this aggregate is going to be durably stored as a state storage type. So we are going to capture only the current state of the aggregate and store it to our database. Now, when we want to handle certain commands, such as, for example, subscription and unsubscription, what we need to do in order to handle them, we need to load the whole state of the aggregate, right? And for this subscription and unsubscription, it makes sense, right? We need everything to handle them. But what happens when update course capacity command arrives, right? Again, because aggregate is a unit of consistency, we need to load everything. However, for updating course capacity, we don't need subscriptions, right? It has nothing to do with subscriptions. Nevertheless, we need to load everything, and it feels a little bit too much. Now, when we move from the state storage world to the event-sourced world, when the state of our aggregate is stored as a series of events, the story is somewhat similar. For handling subscribe and unsubscribe student to course command, we need to load all events that were published by this aggregate. But we also need to load all events when it comes to the update course capacity command. And you can, again, have the same feeling. Why do we need to load subscription and unsubscription events when we have nothing to do with them?
So let's add a new business rule. The course title can change anytime to any title different from the current one. So back to the board. What we need to do is to introduce a new event. Of course, the course has been renamed, triggered by a new command. That is pretty simple. Can somebody guess which aggregate should this commanded event belong to? Anybody? Of course.
Of course.
Of course. So it's very reasonable that course is the most obvious answer in this concept. And the course aggregate is now responsible for something more. It's a little bit larger than before, right? It may seem irrelevant, but it hides a pitfall. Let me introduce the third villain in our story. So the larger the aggregate, the greater the contention. So our natural attitude to identify the aggregate into the business concept of our mental model of the domain lead us to a sometimes unnecessary expansion of the aggregate boundary. Because, of course, anytime we have a new event or of a new command, and this new event or command relates to a concept that is represented by an aggregate, we tend to assign them to it. And it is, anyway, very important to remember that the boundary of consistencies is also the boundary of concurrency. And this is the reason why the sizing, the correct sizing of the aggregate is so important, because it can affect the performance of our application. We can absurdly decide to model our system with a unique single huge aggregate. But this would prevent any form of concurrent access, because all operations should be performed sequentially, since they relate to this aggregate that acts as a contention point. And of course, this is not what we want. So let's make an example. Let's suppose that at the very same time, our system received two commands that are related to the same instance of the course. The first command is to update, is a request for updating the course capacity. The second command is a request for rename the course. And our instinct immediately tells us that they will not conflict, because they do not influence each other, right? So both commands are handled at the same time. That basically means that two replicas of the same aggregate are loaded at the very same time from the repository, and they are updated. Each of them is updated accordingly to their respective command. And the problem arises when we try to persist the transaction, because since the aggregate is the guardian of the invariance, is responsible for the consistency inside the aggregate itself, we cannot accept to concurrent modification. So while the first one will be accepted, the second one will be necessarily rejected. So it doesn't matter that within the aggregate, the two information belongs to two independent group of data, right? It doesn't matter that we know that the renaming the title of the course will never affect the update of the capacity, as well as the opposite. The only fact that they are handled by the same aggregate is sufficient to prevent them from being executed simultaneously. So assigning both of these commands to the same aggregate means increasing the contention in a way that is not necessary, because we know that these two operations could be performed in parallel, but because they are handled by the same aggregate, they must be performed sequentially.
Okay, Sara was complaining a lot about this contention. Let's try to solve this issue. Let's try to propose alternative approach. So instead of having a single aggregate, let's move to two aggregates. What those would be? So one would be for handling course subscriptions, so it knows only about subscriptions, and the other one would be for caring about course details, right? We call it here course info. There are benefits and drawbacks for both approaches. So with the single aggregate approach, with the course only, we have more contention. Sara explained that. But this concept is simpler, right? It is simpler because we have only one thing to maintain, only one thing to manage. When it comes to course info and course subscriptions, so multiple aggregate approach, we have less contention because now commands will go to corresponding aggregates, loading only what they need to be handled. But this adds additional complexity. Now we need to manage multiple aggregates. Imagine the case where you want to create a course. Now instead of creating a course, you need to create course info and course subscriptions. What happens if one of those two creations fail? You need to roll back the other one. Also counts for deletion. If I delete course, I also need to delete all of its subscriptions. So it gets a little bit more complex. So let's say that we had a single aggregate approach, it is deployed in production, we discovered that we have a lot of contention, right? Now we want to refactor our single aggregate approach to two aggregate approach. What this basically means, it means that our model changes and our data is already persisted and durably stored. What are we going to do? If we are in the state persisted world, so that might not be too difficult to implement. So what we need usually to do if we are in SQL world, we just write a SQL script, it goes, updates relations, updates the columns, etc., we are happy. Sometimes it cannot be so easy also in the state persisted world, because we may choose an option to be flexible and to serialize the state of our aggregate in a blob, JSON, XML, or some binary format. Then updating the structure becomes more difficult. There are database tools that can do that, but it is not that trivial. Okay, so far we are covered somehow, but what happens when we come to the event sourcing world? This is super difficult, right? Because in event sourcing, we know that our event stream is immutable. Events are not to be deleted, not to be modified. We shouldn't just all of a sudden insert new events in the stream, etc., etc. So it becomes more complex. Let's take a look at the example. Here we have course created, renamed, and its capacity changed. Now, this is a single aggregate approach. If you want to refactor this, you want to change our event stream, what we need to do is, instead of course created, we need to have two aggregates now, so we need two events for those. The ownership of these events is also going to be different. And then we just go and assign corresponding events to corresponding aggregates. Course renamed belongs to course info, and course capacity changed belongs to course subscriptions aggregate. In events, so basically for this to be possible, you must have an event store that is capable to do so, right? And there aren't that many in the market that can do tricks like this. So this is our fourth villain, I believe, which says that aggregates are difficult to refactor. It is not impossible. There are tools to be done, but definitely not a breeze to be done.
Okay, let's add some more spice to our exercise, introducing another new rule. The student cannot join more than 10 courses. Back to the board. Of course, we have a new event that the student has been created with its respective command. So far, so good. But now things get complicated because I need a new event to subscribe the student to course and a new event for unsubscribe the students from the course. And of course, their respective commands. So, do you also have a sense of déjà vu? You should, because we have seen, we have already met two very similar events and commands when we were talking about the course. But now, I need two more, because the new rule that I need to enforce is about the student aggregates, a new aggregate. So, why should I need two events that basically contain exactly the same concept to represent one single event in the real world? Because life is tough and we have two different aggregates, so we need two events. So here is our new student aggregate. It can handle some commands and it can produce some event, emit some events. And also the aggregate, the student aggregate, exactly as the course aggregate, it contains the subscription that are necessary to make decision about all the subsequent subscription and unsubscription requests. So this situation requires some form of synchronization. Indeed, anytime now we have a request to subscribe a student to a course, this request must be handled by a component that is able to dispatch the respective commands to the student and to the course. The student and the course can then publish their respective events. Easy, until one of the two aggregates decide to refuse the command. For example, if the course is fully booked. So in this case, what we have, the orchestrator component must react accordingly. In this case, for example, by sending another command to the student in order to cancel the previous subscription. So this is one of the possible solutions. There are other possible solutions. But in any way, we introduce complexity. We add some form of synchronization that increases the complexity of the solution. And here you are, the fifth and final villain of our story. Transactions that span multiple aggregates could cause unnecessary complexity. So the main aspect underlying the idea of the aggregate is the concept of boundary. The aggregate is the boundary of consistency, is the boundary of concurrency, but most of all is the boundary of complexity. One of the ideas behind the aggregate was to force the developer to feel this friction, right? To create this small bubble that are isolated from each other in order to to create a minimum context where it's easy to make decision inside this minimum context. So this concept is perfectly in line with the good programming practices like decoupling and high cohesion, but in some cases can increase the complexity, especially when the constraints spans between multiple aggregates. So you can answer me, but that is just a long transaction. What is wrong with that? Nothing is wrong with that, and certainly is a very common situation whenever the long transaction happens between two bounded contexts. But I'm wondering, it is really necessary to introduce this complexity when the long transaction happens in between two aggregates inside the same software component, inside the same bounded context. So it is possible to find a better solution and to avoid this complexity. We will see. So here they are, all the villain, all the bad aspects of our aggregate. The aggregate does not fit storytelling. It moves the focus away from behavior back to the data structure, to the model. It mixes technical and business aspects. It can cause unnecessary contention and unnecessary complexity, and it is hard to refactor. So we just need to shoot it down.
Yeah, so we've been thinking about this. Can we have a better solution when it comes to command modeling? And we decided that we cannot, so this is the end of the presentation. Yeah, jokingly, of course. We tried to move our focus from structure to the behavior. So let's try to see how that would look like. We can observe our system as a series of actions and reactions, right? Actions could be commands, reactions could be events. Doesn't matter in this scenario. What ties those two together are basically some decision blocks. Something that knows how to react to something and provide a reaction. As a decision block, we can have a human, a lady in this case, and she can, based on her experience, and also maybe based on some inquiries from the system, decide to take an action, to change something with the system, to issue a command. Then, similarly, we can also have a decision block represented by the software component, right? And similarly, software component can also learn from the system. It can load the data necessary for it to make the decision, to react on the action. And it can decide, okay, I'm going to load what I need. This is the thing that I need to do, so I'm just going to do it, right? And I'm going to provide the reaction. So now we are going to focus on the decision. And the decision maker in this case would be the message handler, right? And message handler is the one that knows what it needs to take this decision. Another little helper, or maybe not so little, that will try to help us here is the event sourcing. Why is that? Because event sourcing decouples persistence from the model needed for taking this decision, right? Event sourcing is basically just storing the state of the system in a series of events published. What this also means for us that message handler can now build on the fly any model that it needs based on the event stream that is already persisted. Let's take a look at the example. So here we have events published by student, published by course, and now we have a command that we need to handle, that is to update the course capacity. Earlier, with aggregate, we needed to load all these three events, because aggregate is a unit of consistency. We need them all to calculate the current state. When you take a look at our command handler and our decision block, what it says, I just need to check whether the course exists and whether the new capacity is different from the previous one. So why do I need the event in the middle? And the fact is, I don't. So I'm not going to load it. Basically, I'm just going to the event store and I'm going to read only necessary events, and based on them, I may choose to publish a reaction, so to publish an event to the event store, or just to refuse it. When it comes to the event store, we should take a look at the event store with a little bit different eyes. So instead of streaming events for specific aggregate identifier, we are going to introduce another approach to stream events based on certain query. Let's zoom into this query. So it is comprised of domain identifiers, so what we are interested in from our domain. In our case, that's a course with its corresponding ID. But we do not need everything from the course, right? Then we can filter even further and provide types that we are interested in. In our specific case, there's a course created and course capacity changed. And these two together will form a stream query. Again, the focus is now on the message handler. This means that we are going to have less waste of resources. So when it comes to CPU, to memory, to network bandwidth, etc., just by loading less data, we will come to the situation where we are more mindful towards resources. We don't need to think in our design phase what is the structure of our model. And we don't need to be married, especially in the event sourcing world. We don't have to be married to this model for until we try to refactor. And it gives us more flexibility, because now we dynamically can go to our message handlers, to our decision blocks, and change the data that we need and how we are going to create the command model based on those.
Okay, let's move back to my favorite topic, concurrency again. And let's see what happens in case of concurrent write operation. So let's assume this is our event store representation, and let's assume that the system receives the command to update the capacity and the command for updating the title at the very same time. And our instinct immediately tells us there will be no conflicts because these two operations does not interfere with each other, right? So the two blocks can, based on the query that Milan just explained, load their stream, their respective stream, reconstruct their state, the state models needed to make a decision, and then finally can publish their respective events. So far, so good, very simple. Let's now see what happens when the system receives at the same time the command to subscribe a student to a course and the command to update the course capacity of the same course. In this case, we have a problem. The risk of collision exists. So let's say that the two blocks are able to load at the same time their respective event stream needed for recreate a state, a model to make a decision. Then the first block that is able to publish an event, let's say that is the one related to the update of the capacity. Just a few milliseconds later, the other blocks publishes the subscription event. But in this case, however, it could happen that the capacity update that was published just a few milliseconds before could invalidate the choice made about the subscription. It could be that it reduced the capacity enough to prevent the subscription to happen, right? So the course capacity change event had not been considered, this last one, when the decision block has loaded the event stream to reconstruct the model. So it is not aware of this last event. Let's see how we can handle this situation. So I'm a little bit excited here because I believe that this is a revolutionary idea that can really allow us to avoid the aggregate and to replace it with a better option. So instead of having the regular append events that normally each event store provides, we want to have another API, the conditional append. So how does it work? The conditional append requires two additional parameters besides the events to be appended, of course. The first one is the stream query, and the second one is the identifier of the last event. So let me explain them. The stream query was it's the query that was used to load the model needed for making the decision that ended up in the publication of these events. And the last event identifier is the last event, the identifier of the last event included in that model. So what are these parameters needed for? They are needed to ensure, to guarantee that the decision is made on the most up-to-date data. Basically to ensure that there is no new event after the last expected one that could affect my decision. So in other words, that there is no new event matching the query after the identifier of the last event that I'm expecting to have. So if the last event identifier, or if the identifier of the last event returned by the query at the time of the append is different from the expected one, doesn't match the one that was provided as a parameter of the conditional append, it means that the decision made is potentially wrong because it is based on out-of-date data. I may have decided to, for example, accept a student subscription when just a few milliseconds before the capacity was decreased to prevent that subscription. So in this case, the append is rejected. And the condition is not satisfied, so the conditional append, the event store must reject this append. And the decision block can then decide to load the remaining part of the stream or to reload completely the model and to try again and to make again the decision with a state model that would be necessary, most up-to-date than before. So in practice, the conditional append represents the guarantee that an event or a group of events is published, is appended if and only if the event store does not contain any events that match the query after the expected last event. It represents the guarantee that the decision has been made on the basis of the most up-to-date data. It basically represents a form of optimistic lock specific for event sourcing systems. So let's go back to the practical example. these two blocks has loaded their own stream and reconstructed their own data structure to make a decision, and they both loaded as last event the number 592. So now the first block to invoke the conditional append is the one related to the update curse capacity command, right? And since the last event it loaded was the number 592, the event store checks that at the time of the append there are no events after 592 that would have been part of the query. And since there are not, the append is accepted and the event is stored. When the subscribe to student commands handler tried to publish its events, it also used the conditional append. And it also loaded as last event the number 592. This time, the event store checks that at the time of the append, there is an event, the number 593, that is following the 592 and which is part of the query. So in this case, the event store rejects the append.
And now, with this approach, we already saw that we do not need to load a lot of events, right? So basically, our contention is going to be narrowed down to only what is necessary. When we compare it to aggregate approach, we have now, in the aggregate approach, we had boundaries of the aggregate, and now we have the boundaries of the stream query. And now we can have that benefit, and that's really cool, but we can go even further. Let's take a look at the déjà vu example that Sara was mentioning, right? We have subscribe student to course command and event, both, and unsubscribe, of course, belonging both to the course and to the student. This, I mean, during the design phase already looks a little bit artificial and not so good, right? Then when we go to the event store, when we see how our events are persisted, we again see these two events, basically duplicates. What's different about them is the ownership. When a business expert comes and asks, okay, why is that? It is difficult for us to explain, right? They represent the same fact. But the reason why we need them, because we want to guard the invariance for both of the aggregates. So we have a technical reason, we don't have a business reason, but it will live in our event store forever. When we go back to the storytelling perspective, it is basically just two facts. Students subscribed, student unsubscribed, we have commands, and we have decision blocks connecting those two together. Let's now try to see how we can work on this example and improve it even further. This is the event store. Firstly, what we are going to do is we are going to remove the ownership. We do not want to know in our event store about aggregates. So we're going to have only pure events, only facts that have happened in our system. But again, we need a way to correlate these facts to specific domain concepts. So we are going to say, let's have domain identifiers pointing to those concepts. Let's remove the ownership, and let's have something that we call tags or domain identifiers. It really doesn't matter. What is important is that they can just point to different domain concepts. In our case, we have course and student. So what we can do now is just, we have two events that basically represent the same fact. We have two domain concepts pointing to those events. We can just merge them together, and we can say, now we're going to have a single event, but we're going to have two pointers to the same event.
And this grants us another exceptional advantage. Let's find out with an example. So let's see how our system behaves when it receives the command for subscribing a student to a course. So we know that our decision block is responsible for making a decision, and the decision block is aware of the business rule that we need to respect for making a decision. So it's aware that the course cannot accept more than 10 students, and is aware that the student cannot join more than 10 courses. So if both of these rules are not violated, the block can decide to publish the event, student subscribed to course event. So now we can take advantage of the flexibility of the query, and we can retrieve at the same time, in the same stream, both events from the student and the course that are needed to make this decision in a single stream. Then the command handler is able to reconstruct the model based on the query, and based on that model is able to verify in a single moment, in a single place, that the subscription does not violate both business rules, so that the maximum number of students per course is not violated, nor the maximum number of course per student in the very same time. And if both rules are validated, it will be possible to publish a single event that is related, however, to both those business elements, to the course and the students. So therefore, the event store should not be able only to append new events, but new domain events, where the domain events is nothing more than the pair formed by the pure event and a collection of domain identifiers matched to it. So in my example, the domain identifier is expressed by a key value pair, but where the key represents the concept, right? The course concept, the student concept, and the value represented the instance, so the single instance of this concept, but it can be anything. It's just an example. Anything that is unique in the bounded context is valid. And the domain identifiers are matched to the single events. It is possible to have in the same transaction more than one event published, and each of them can have different domain identifiers bound to it. So, for example, let's make an example. If after a student is subscribed to a course, the course reached its maximum capacity, I may want to publish, for example, the course fully booked event in the same transaction. And the student subscribed to course event will be associated with both student and the course, while the course fully booked event will be associated only with the course. So let's try to translate this into pseudocode. I want to append two events in the same transaction: student subscribed to course event associated with both student and course domain identifier, and course fully booked event associated only with the course domain identifier. The stream query is the query that I used to build the data structure, the model needed for making that decision. And the last event is the identifier of the last event that was included in the rebuild of this model. If the query, at the time of the append, returns a last event that is different from the expected one, it just means that the decision was made on incomplete data, not on the most up-to-date model. So in this case, the append would be rejected.
Now let's zoom into these pure events that we mentioned a few slides earlier. So basically, they represent more realistic view on the world that we have. Some characteristics that they have is that they do not belong to anyone, right? They are just facts that have happened in the business that are important to the business, not technical facts. And they can be related to one or more domain concepts. So this is also really important to avoid duplication. Let's see what benefits we can extract from this. We have less complexity, right? There is no owner. The business decision now can easily involve several domain concepts. What this means, if you remember Sara's example about the coordination between two aggregates, right? We don't need that anymore. And the decision is taken in a single place. So earlier we needed to coordinate this long business transaction between several aggregates. Now we don't have to, because we can do it in single message handler. We just need to load the data that we need. However, when we want to go across bounded context, when we need to synchronize between several bounded contexts, this synchronization is still needed, because we don't want to lock two bounded contexts into a single message handler. The other benefit is more flexibility. Again, event sourcing decouples the persistence from the model. It gives us really great flexibility also when it comes to refactoring. So now when we want to change our model, we just basically need to change the stream query, so the events that we are interested, or add or remove domain identifiers.
So the aggregate is finally dead, together with all the negative aspects associated with it. And this new approach that we decided to call the dynamic consistency boundary, or DCB for friends, it integrates naturally into the storytelling. It focuses on the behavior instead of the model. It reduces the contention, basically. It reduces the complexity, and it simplifies the refactoring. So the aggregate is dead, but be careful, because this does not mean that you should model your system with hundreds of command handler completely correlated, completely unrelated between each other, right? Absolutely not. So clustering commands into logical groups and delegating their execution to the same model is and remain a valid approach, a correct programming approach. So the difference lies in the fact that by the very definition of the aggregate, this model necessarily had to be isolated from each other. Now, killing the aggregate means to admit the possibility of contamination between these models without renouncing consistency. Basically, a less dogmatic approach that, in any case, must not disregard the good programming practices, but that, thanks to a greater flexibility, it allows the better model to evolve during time, to evolve in time, right? And to emerge over time. So basically, the ability to create this intersection must not be exploited in all cases, in all situations. There will be a lot of situations where this is not needed. And of course, as always, there is no single answer, there is no single truth, but every tool must be used with pragmatism and common sense when it is needed. So, thank you.